Hi. So welcome back. In the last video, you might have noticed that I didn't have audio in the second third of the video portion because I made a blunder while recording it, and I didn't want to reshoot everything, re-record everything again. So I just uploaded it as is with some background music. Right now, what I'll do is I'll walk through quickly over those parts of the coding that we did in last video and then move along from there. So basically, till the point where audio is present in the video, we have prepared the data loader, which would give us basically 2 by 4 tensor, uh, where 2 is the batch dimension and 4 is the time dimension, or basically block size. Then we made a, so this was our get batch function. We should do that. Here, batch size is 32, I believe. So that's why it's we are getting such a big tensor. And you see every element in the batch will have four different four different training examples because our block size was 4 at that point. So from then there we built a class of bigram language model by inheriting from an dot module. So we kept the model as simple as possible with just an embedding layer, which would take in vocab size as the input and output the logits of length vocab size. Using that, we would in the forward method we would create logits. Then we would create loss if targets were present. So if targets were present, there could be two ways of creating loss. Basically, ideally, we'll have to transform logits and targets in a way that the uh, dimensions align such that they follow the requirement of f dot cross entropy function. So therefore, this is the two ways of doing it. One is you just transpose logits, last two dimensions of it, and you pass it on to f dot cross entropy. Otherwise, you reduce your dimensions from 3 to 2 in logits, b by t times c instead of b times t times c, and targets as just one dimensional vector b times t in the vector. So and then if you pass it to law, f dot cross entropy, it will again calculate loss. We used more or less the same generate method that we were using in our uh, earlier videos in the series. So we pass on the IDX, which is of dimension b by t. We pass this IDX to the model. So we get the logits of shape b by vocab size. Here there's basically, uh, I should say it should be of 2 by b by t by vocab size. And then we index into the last time step of that logits, because here we are doing bigram modeling. So we need only one time step, last time step, to predict the next character. So this becomes a b by vocab size tensor. From there we pass it to f dot softmax along the last dimension, and we get probabilities for b different b samples in the batch. Taussig multinomial will help us predict next index out of from this probability number of samples one, and then we concatenate the new index into the our old IDX. So it will become b by t plus 1, and we do continue doing so for max new token times. Then we tried running the model. So basically it would just generate some gibberish because it is not yet trained. So then we next thought of training it. We initialize our optimizer, uh, our hyperparameters like max iterations that we want to train it for, batch size which is 32. Then within the iteration loop, training loop, we are calling get batch function every time to get a new batch of data. We're calculating logits and loss with a forward pass. Then we zero our gradients, call backward, which would just fill in the gradients with a backward pass. Take a step to update the weights or parameters of the model, and then print the loss. So by the end of 10,000 iterations, we were able to reach 2.3 loss value, and this is what we are generating at that point. So then we thought of complexifying the forward um, pass in the model a bit. Before that, we wrote a function to evaluate loss, basically for each train and validation split. Because right now there's in this point while training the model, we don't have any good way of printing the loss for train and validation set. We were just printing it once at the end. So instead, we thought that at certain interval, we'll print loss for train and validation sets. So we wrote this function where we um, define a dictionary, initialize a empty dictionary out, and we put the model in eval mode. For each split, train and val, we initialize zeros with eval iters length, which is nothing but a number of batches that we aggregate for getting a loss at that particular interval. For that eval iter times, we get a batch from that split. We calculate loss using the model. We put the loss number into the losses at the kth index. So once we have all of these elements in the losses field, we take a mean of it to put it into out of a split. So once let's go on and we will see how that is being used. So now we have put a extra diversion into this bigram language model, more or less, mostly it is same, but we have added a LM head here. So instead of directly going to logits from a token embedding table, um, we go into a n-dimensional representation from embedding, and n-dimensional n embed is transformed to logits of vocab size now. So this is what we have added here. Rest of the things are same. So we initialize the model, initialize the optimizer, and then we train it for again 10,000 iterations. So here we have used if iteration number, current running iteration is percentage width is divisible by eval interval, which is it's 1,000. So every 1,000 interval, every 1,000 iteration, 1,000th iteration, we are going to print estimate our loss, and we are going to print out of train means which is train loss, and out of val, which is validation loss. That's what you see here, the printing is going on. So the best we are able to reach is 2.4944 as of now. So we tried using that model to print again, and still it's more or less gibberish. So from here, I want to get into the uh, details of implementing GPT kind of model. This framework would be more or less same, but we'll keep on adding components to the forward pass. Okay, so I just ported all of that code into a .py file so that we can run it directly with a script. So here are the hyperparameters that we are using. Device is a hyperparameter I defined to choose if we have a GPU device in a system or not. If not, then we'll use CPU as the device. So block size, batch size, eval iters, eval interval, and max iterations are the parameters that we are using, that we'll use. We are loading the data, creating a vocabulary, vocab size, mappings from string to index and the reverse mapping, encode function and the decode function, data split between train and val data, get batch function that will give us a batch of data of batch size. Estimate loss function that will help us estimate train and validation loss at certain interval while training the model. Then we'll have a model class. So it's same thing as we just discussed, ported here. Initializing the model and optimizer. One thing different I've done here is varying the learning rate. So learning rate we are keeping as 1e minus 3 if it is less than 10,000 iteration, else 1e minus 4. So this is a way of varying the learning rate and optimize param groups. Forward pass, getting a batch of data, forward pass, backward pass, and yeah, printing of the loss. So yes, let's see. Before looking at it, how do I take this up? Okay, so I tried multiple stages of training, multiple maximum iteration numbers. So at a point, certain point, I was noticing that it wasn't reducing below 2.4, that ballpark, 2.49, 2.48. Even with 10,000 iterations, we could reach 2.49, but after varying the learning rate, we were still not able to reach, go further down that number, even with more iterations. So I think for now we can just keep this um, commented out, and we'll just use the learning rate of 1e minus 3 for 10,000 iterations. So we can just run it here. Okay, sorry, my bad. So we are training it now. You see, this is the generation, and our validation loss we best we could do is 2.53 we could reach. So yeah, we are not doing very well as of now. Um, to do that, to improve it, I'll just quickly push it in. So I'm also checking, pushing it. I'll keep adding the every small commits into the repo so that this can be tracked later. So now let's start with the changes to improve this model. So basically, you see, we are creating a diversion from vocab size embeddings to an embed size embeddings, and then we are transforming it into logits of vocab size. So instead of using just a token embedding table, embedding the tokens individually, what we could instead also do is we can create a embedding that gives some significance to the position of that token. Basically, let's say if a block size is of 8, then each of those 8 positions, if they have their own significance or their own representation, it can add value to the representation, final representation of the token, basically. So let's say we create position embedding table and then dot. So basically, we'll just create another embedding layer of size block size by an embed. So because here we are mapping every position in a block size to an embed dimensional embeddings, our input will be block size, and LM head would be same as before. Here in forward pass, instead what we'll do extra is uh, position embedding would be self dot position embedding table. So we have to give input to this would be um, second dimension would be range block size So yeah, so if we do a torch dot arrange for size. Okay, doing this using a global block size here means we'll always be getting position embedding for 8 time steps. But we'll also have situations where our inputs are of time steps lesser than 8 because we are preparing our input in that fashion, right? So let's unpack batch and time dimensions from X, and instead let's use T here and define allocate this to device. This would give us a batch by T by an embed. So we create input with token embedding plus token embeddings plus position embeddings, and we pass it to LM head. And this gives us a better routing, better representation. We expect this to give us a better representation. So let's take it for a spin and let's see if we somehow are able to get better loss. 2.49, 2.5 is what we were achieving earlier. Oh, okay. Okay, so we are getting this issue here right now because index out of range, because at this point, uh, so we should get a index out of range error now while generation, index out of range. So basically what's happening is when we are doing calling generate function here it goes into the generate, and what we are doing here is for each IDX. IDX can be longer than or smaller than or lesser than. The idea is we need to crop the IDX to get only last T time steps or block size time steps. If we get IDX that is of T value that is more than block size, it would be a problem for our model because we have now included position in the embedding table, which would take only maximum block size inputs. Therefore, what we do is we take all the rows here and take from minus last block size time steps in this. Now it should run. It should generate as well. I mean, cool. So we are generating. Uh, we don't see much any improvement in the loss numbers, significant improvement, but it is functioning properly now. Okay, so next up, let's talk about self-attention. That is the next component we are going to um, plug into our language model that we built in the last video. Before going into plugging the self-attention, let's incrementally build up to a single head of self-attention. How do we do it? So basically, first let's take a look at the data that is going into a language model class right now. Um, if the batch size is 4 and the block size or context length is 8, we get an input x of size 4 by 8. This is an input which has 4 different um, sequences in this batch, one sequence, two sequence, and so on. Then each sequence has 8 different tokens as per the maximum window we have. But what we want our model to look at is it should treat this one sequence of 8 tokens as 8 different inputs. First input is only one token going as an input and the next as output. Second input is only these first two tokens go in as input and third is the output, and so on. And the last eighth input would be all 8 tokens go in at input as and the eighth would be the output. To so this is how one sequence in a batch broken up into 8 different examples would look like, but we are not explicitly making them in this way and sending it to the model right now, because right now we are just doing a bigram language modeling, and per token level we are transforming it into a logits equal to the of length vocab size, and then we are sampling using it. We were creating some diversion to reach to the point of logits, and then we are using that logits for each token and sampling basically. So now, how do we use attention to tell network that you have these many inputs and they're of different length and the targets, and how does the interaction work? So to get to that point, let's start with a sample. We define our BTC, batch and time and channel dimensions as 4, 8, 2. We initialize as random numbers, input x. So our input looks like is of shape 4 by 8 by 2. A batch will have 4 samples, 8 time 8 sequence in each sample, and 2 is the context, is the channel size or the uh, representation of each token is done in two-dimensional vector. So let's look at the 0th sample, the first sample in our batch. This is how it looks like. It is basically a 8 by 2 dimensional matrix. So each row here is a token. This is the 0th token, first token, and 7th token. So each token is represented in two-dimensional vector. Now what we want to do is we want to do two things. First is to break to transform this 4 by 8 by 2 tensor into a way that it represents 8 different inputs, first thing, and 8 different inputs in a way that first input, only first token is going in as input. Um, so it should have interactions between that particular input. The second input that goes into the model would be first two tokens. So there should be interaction between these two tokens, and interaction in a way that uh, that has to be learned by the model. Then third input uh, uh, has to be an interaction between first three tokens. So basically, the trend is that at any time step that goes into the model, uh, it has an interaction between all the tokens that come before that particular token t at time step t, and it has interaction between all preceding um, tokens and their representations. So to do so, I have a snippet here. What we are doing is, in a naive way, is so this is what I want to represent the representation with the new representation, how the which would indicate the which would go in the model with the impression that the first token in zeroth batch in the zeroth sample in the batch would be nothing but the token, it's the that particular token's representation itself. Next token would go is, it would have interaction between two different tokens, zeroth and first token representations. So we are iterating for each sample in the batch. Then we are iterating over each time step. So we take all the previous array of tensor of inputs would be at this batch dimension indexed and sliced till t plus one time step. So that is basically 0 till t time steps. We will get all the columns. So that gives us a output of matrix T by C, where T is time step at this current point in range T, and C is dimensional size. So C is, for sake of purpose, it's 2 that we are assuming. So now what we are doing is, here basically we are trying to understand how the interaction will happen. We'll go ahead and understand how the learning of the interactions or dynamic calculation of the interactions will be done later. But most naive way would be to add up all those tokens from 0 till t time step and their representations to make a vector of c dimension. And then you put that particular vector of interaction vector into that the position of b by t, b and t index. So we index this T by C dimensional matrix of previous inputs, and we sum them by dimension 0. So all the T dimensions are summed together. So let's say T by C is the T is the rows and C is the column. So we are summing along the dimension 0, which is T. So this will give us a c-dimensional vector, which would be a representation of interaction between all t sequence, all the tokens in the sequence of length t, a small t basically, which is in the range of capital T. So this would be a c length vector, and then we assign it to uh, b comma t index position in x bow. So we calculate this. Now, if you see what let's look at x bow 0. So basically, x bow 0 is a new representation come out of x. So I want to look at the x bow 0. Basically, what's happening going on in here is, if you compare x0 and x bow 0, x bow 0 is basically a bag of words version of x, wherein we are sequentially, incrementally interacting, summing up all the values in the channel C across all the time dimensions for each sequence. So this is the first sample in batch X. This is also the first sample. So the size of both are same. It's 8 by 2. And you see the first element in this matrix is the at the first time step, what is the representation look like right now is exactly the same as in the X, because we had nothing to add. It was just single input at that point. Assume that when t was 0, so 0 till 1, this would index only one vector, only one column of out of t by c. So it would have been 1 by c. So there was nothing to add. So this is exactly same as the x of 0, 0. Now, when you see this, this should be equal to, um, let's say, first time step of this should be equal to x of 0, 0 plus x of 0, 1. So these two should be equal. This should be equal to summation of this number and this number and this number and this number. Let's see if this comes out to be true. So yeah, both these are true, means uh, so basically this representation of at the second position is a sum of these two inputs. So basically at the second input that goes into the model would be interaction between the first token and the second token. Right now the interaction is simple addition and we'll complexify it, but that's how it will work. So the last input here would be the sum of all of these elements by time dimension. So these elements form first input, these elements for second element in the vector C, vector of length C. That's how it would work. So if we see, so this is x bow of 0. Now you see we are doing this very inefficiently, wherein we are iterating with for loops across two different dimensions and then calculating the sum, etc. A better way of doing this would be, let's call it method 2, is we can do this through efficiently through matrix multiplication. So what's happening here is, um, let's make a way matrix of torch dot ones of shape t by t, or rather they should be c by c. No, they should be t by t. And so this would give us a matrix of 1 by 1, 1 all at all t by t positions. So if we wrap this into a torch function called torch.trail, this would give us a lower triangular matrix basically. So this is what it becomes. All the elements in the upper triangle get 0. So this is something that is going to help us represent our data in the form that first input would have interaction only from first element of that first token of the uh, 0th batch and 0th sample and 0th token. Then this would have interaction from first two tokens and so on, and the last input would have interaction between all tokens. How this is going to help us is, if we do weigh, so so what is weigh going to do is, this is a t by t matrix multiplied with b by t by c. So this would do a batch matrix multiplication. It would create a batch dimension here, dummy batch dimension, and it would multiply t by t and t by c. So it would give us a b by t by c. So this is basically t by t matrix multiplied with t by c matrix, and it would give us a t by c output, and for each element in the batch. Uh, let's say we call it out. Out dot shapes should be b by t by c, which is 4 by 8 by 2. Instead, let's also call it expo2. We are calculating expo with a different method, right? So expo2. So you see, if you look at the zeroth element of expo2, it should come very close to expo. It should come very close to expo zeroth element, 1.7236 minus 12030, 1.5302, 0.2071. So these are exactly same. If you want to verify it, we can say expo equal to expo 2. This may or may not give us true um, because it is uh, uh, floating point arithmetic may differ slightly, which might not equate always. So you see some falses are there. But to negate that, we can see if we can use a function called torch.allClose. And if it is very close to each other, each element in these, it should give us true. Um, sorry. Yes, so most of the all the elements are very close to each other. That confirms. So what we just did here is we use this lower triangular matrix with all one to calculate the interaction between the tokens incrementally. This interaction between first token, interaction between first two tokens, first three tokens, and the first all the eight tokens. That's what we do, and we matrix multiply this with the egg input. So it would just give us the output of x02. So another thing we can, as a next step, we can do here is we can, instead of just getting all these interactions as a direct sum of the uh, tokens from 0 till t position, we can instead do a mean of those position tokens across all the channels. So let's say what we do is we divide it by sum, and at the dimension way is nothing but t by t. So across this dimension, if we take the sum and normalize it, so this would become 1, this would be 0 0.5, 0 0.5, 0 0.3, 0 0.3, 0 0.3, and so on. So across dimension 1, then our way should look something like, wait, I must keep the equals to 2. So this would give us a new way matrix, which is 1, 0 0.5, 0 0.5, 0.33, 0.33, and so on. And last one is equally distributed across all. So what this will do is this will give us a mean instead of some interaction. So if we now do this, we would get something different. So now we are doing mean here. This would not work now because our this first calculation here was some. If we take a mean here, this should still come out true. So now that we have a summation, a way of doing interaction as a mean between all the previous tokens, let's go ahead and also get one last way of understand one last way of doing it, which is using softmax function. So let's say we have a way matrix which is torch dot trill torch dot ones t comma t. If we have this way matrix, or instead, let's say we have a not this way. Let's say we have a torch dot ones t comma t. So this is what a looks like. Now, this is what a looks like. We initialize a wave matrix. So it's better if we, let's say we call it a trill variable. This is what trill looks like. We initialize a way, which is nothing but toss dot zeros t by t. This is what a way would look like. Now, if we do something like way dot mask fill with masking as trill equals to 0, and where it is 0, we are filling it as minus infinity. So just look at how our way would change. This would fill the way matrix with minus infinities wherever that trill was 0. Now if we want to make it as this matrix, this would give us we would have to do something like f dot or way equals to f dot softmax way dimension equals to we want to do this across this dimension, so we just say dimension -1. And then if we look at way, what it should give us is something similar to what we are getting way here. It would be a normalized version of the ways. Cool. Yeah, so we have 1 here, remaining element 0. We have 0.5, 0.5 first two places, then zeros. We have 0.3, 0.3, 0.3, then all zeros, and so on. So we got something similar. And now if we do x bow tree to way at matrix multiplied with x, we should get something similar. Dot dot all close x bow tree. It should give us true. So this is much efficient way of doing this, because uh, softmax internally is very numerically stable uh, calculations, so this should not give us any problem, and efficient way of doing things as well. Now what we have done is we have found a way of representing a input of b by t by c shape into a transformed version of x bow of same shape, but with each sample in a each token representation in a sample, uh, giving representations of interaction between that particular position and all the preceding positions, those preceding tokens. That's what it represents right now. So now that we have this, what we need to do is a way of calculating this weight matrix, and how to calculate this weight matrix, and how do we basically transform our x using this weight matrix. Right now, what this way represents is a weighted aggregation of the inputs. So basically, when we initialized way with zeros and we filled with minus infinity all the zero positions wherever trill was 0, we were we happen to reach to a point where we are uniformly aggregating all of the inputs. At any instance, let's say all of the first three inputs are equally getting interacted. That means they are getting uniformly averaged out. But we don't want to do that. We want this to be learned, these interactions to be learned with data dependent way, in a data dependent way. So instead, if we initialize this not zeros or randomly, or with some initialization method, we would, and then apply mask fill with trill equal to 0, then we would not be having this uniformity in the aggregation. That's what we want to do, and we want to do it in a data driven way. So to do that, what approach the attention is all you need paper proposes is that we emit two different vectors from each token. One is query and one is key. So each token in the block in the sample would have, and let's say each token in the sample for self-attention purposes would emit two different vectors, query and key. So each this would have a query, its own query and key vector. This would have its own query and key vector, and so on. The query vector of any particular token would interact with key vector of all of the tokens and decide the affinity scores between them. So basically, you have a query vector for token at t0 position. You will interact with key vector of all the positions, all the 8 positions, and you will decide on the affinity scores. So this would basically be a multiplication, dot product between this query vector and key vectors of each position, and that would give us affinity scores. Let's try to do this, how it would look like. This is what we are trying to implement as a single head of self-attention. So let's say we have head or not n head equals to 16. We have our x of shape 4 by 8 by 2. We have so we define two different linear layers, n dot linear of dimension c by n head and query of same dimensional matrix. Now, what will happen is we'll project our input x with query and key. So q equals to key x, k equals to key. Sorry. So this would give us b by t by c x matrix multiplied with b by t by or b by c by n head. There's no batch dimension to it, and this would give us basically a batch matrix multiplication b by t by n head, and something similar would also happen here. So now we have queries and keys. So queries for each sequence in b by t by n head. There are t time steps or t length sequence, and each token is represented by n head dimensional vectors. So this is what a query basically we can say is q of 0, which is 0th first sample in projection of x, queried projection of x, and um, 0th token representation, which is a n head length vector. This is nothing but query for first token in first sample in the batch. This is what it is basically. Uh, so this is all is a query vector for each token in this batch. This would give us this tensor, and this would give us key vector for each position in the batch, each token in the batch. Once we have this, we can calculate way with. So let's turn to our paper right now. Okay, so if you look at this matrix multiplication, this is a scale dot product attention. This is one head of the attention mechanism that we are going to perform. So you see Q and K, which is query and K matrices or tensors coming out of input with projections. They are matrix multiplied and scaled to some level so that they can be. And this softmax and masking is also done to make it get the affinity scores. So you see the calculation being happening here is QKT. Now I'll switch back to the VS Code. What we are going to do is Q matrix multiplied with K dot transpose. Now what essentially we want to do is we want to matrix multiplied Q of this shape with K of this shape. But K has to be of this shape for performing matrix multiplication, and this should give us something like P by T by T, which is nothing but same as way that we are calculating here, way, which is T by T. Right now we are doing way was same for every element in the batch. Therefore, we are forming initializing way as only T by T. But with data-driven approach, it would be calculated differently for each element in the batch depending upon the input, because we are doing this matrix multiplication. And to do this, we have to do K dot transpose -1 and -2. We have to transpose -2 and -2 dimensions. So these two dimensions would get transposed and become n head by t. And therefore we would get way of shape b by t by t, which is 4 by 8 by 8. So now this is our affinity scores. How does it look like? This looks like something like this. So maybe let's take a look at the first element, which is way of 0 is nothing but affinity scores for input for the first sequence in the batch, which is dynamically computed based on the inputs projections and their matrix multiplication. So this right now is not masked. We need to mask the upper triangle part of it for autoregressive purposes, so that we'll have to do it. But yeah, this is what we have right now. So to do that, we'll have to f dot softmax of way at dimension 0, 1, -1. So we'll get f of 0 to be something like this is our way. Now instead first what we do is goes to a dot masked trill equals to 0, float minus infinity. So this is what way looks like now, or rather, let's say minus infinity. Let me calculate this again. This is what way 0 looks like. So we are not doing any softmax right now. We are just masking it with masked fill. So this is what it looks like. First element remains same. The next all elements you get minus infinity, so that we are incrementally masking one token additionally at the time. And if we do softmax, so all these with exponentiation become 0. All these become some number and they get averaged out. So basically what we get now is this. So in the first element, we always get 1 with all the zeros. Next token has interaction at this proportion 0.8 and 0.1. and other all are zero, and all and the last element, last token has interaction, last input has interaction between all tokens in this proportion. That's what we get way zeros. Once we have these way zeros, basically let me copy paste these two lines of code and stick them here. So once we have a masked and normalized way, we can go ahead and calculate our attention scores. So next we can calculate out as matrix multiplication between y and x, which would be b by t by, or rather b by t matrix multiplied with b by t by c. We can do that, and we could get out dot shape as 4 by 8 by 2. But there's a digression in the implementation of this where uh, authors say that we shouldn't directly share private information with the ways, and we should create a digression, one more digression here with a linear combination name as value, which is again n dot linear c by, or rather n head, and we then calculate v to value of x. This would give us b by t by n head dimension. So this would be n head and matrix multiply with v. So this would give us b by t by n head dimensional tensor, b by t by n head, which is 16. So this is what a head of one head of self attention would look like. So basically we'll have query key value linear weight matrices, which would be transposing x with q, k, and v, which would form q, k, and v vectors for each token in a batch. We'll calculate affinity scores on the fly with q matrix multiplied with k transpose, which would give us b by t um, affinity scores, which would be different for each element in the batch, calculated dynamically. And we then mask it and normalize it to mask the tokens from being looped in the future. And then we matrix multiply way with v to get output of that one particular head of the attention. So this is what one head of the attention would look like. Now let's put this into our Python file. So let's implement head of one head of the self attention. We call it as head. We'll take an input head size, which would be the dimension of n head, basically, as in our last explanation. So we'll also have to register a trill function, trill register buffer. So register buffer is a way of registering a variable in the PyTorch modules where the gradients for which are not tracked or which is not included in backpropagation. So we name it as trill and we define it as torch dot trill, torch dot ones of block size by block size. This would be a unpack the dimensions of x. Then we calculate q equals to dot query project v into it. This would be v by t by head size query and key will be self dot key pass with x and v is self dot value x. These all these three projections would be of the same shapes. Now we'll calculate way as Q matrix multiplied with K transpose of -2 -1 way equals to we do way dot must fill till equals to 0. Should say self dot trill is equals to 0 with minus infinity way equals to way dot f dot so max way dimension -1. So what happens here is when we do this, let me write it again. V by T by head size matrix multiplied by V by head size by T give us V by T affinity scores. And this V by T when we are replacing wherever trill is 0 means which is the upper triangle of the matrix with minus infinity, we'll get lower triangle weight affinity scores, and we take a normalize it with softmax across the last dimension, which is across the channel dimensions head size basically. So this would give us affinity scores of size p by t by t. Now we'll calculate out equals to way matrix multiplied with v. So this would give us b by t matrix multiplied with v by t by head size and give us result as b by t by head size. So this would be the output of a one head of the cell potential layer. We return out. We return out, and here now what we do is dot self we create a diversion called self attention head equals to head of head size equals to n head. And this n head would be then, or let's just keep it for with the same size right now. So this n numbered would then go into the linear layer of transforming into logits of vocab size. So token embedding, get X here, we pass X into it. So after adding token embedding and positional embedding here, we pass token embedding to self-attention head. We pass that output of self-attention head to get the logits into the LM head. And this should, I think, work. Let's take it possible. Maybe I scaled it up so much. Let me scale down the parameters. Okay, so this is 8 by 4, 32 by 32. Okay, let's uncomment this one now. Comment this one now. Let's also try to print the size of the parameters. 7,649 parameters. So in our last training, we were able to reach till 2.48, 2.5, 2.48. Let's see if with this addition of one head of self-attention, we are able to do better or not. There was one issue in the generate uh, method for this while training. So you see, while we're calling self octal equals to 0. Out with shape is 111. Doesn't match the broadcast shape of 188. So what is happening here is we have taken directly self trill equals to 0, which is of the shape 8 by 8, block size by block size. But when we are generating, we are just starting to pass a tensor of shape 1 by 1. So instead, what we have to do here is we should index this to in zeroth dimension till value t and in first dimension till value t. So this should give us an index or take a subset of the matrix for the number of time steps that are being given inside here. Yeah. Now let's try to run. All right. So we have successfully implemented a single head of a self-attention. Now we want to implement multi-head version of the attention, which is shown in the paper here. So if you look here, this is what we implemented. Um, Query key value. We did it matrix multiply to get the attention scores, then scaling. Okay, so scaling we didn't do, but let us quickly do that. So what we have to do is, if you look at the formula, this query key transpose is the result of this is divided by a square root of dk. Dk is basically dimension of the input. So query and key output dimensions are dk. So we'll have to divide it with the square root of this, which we'll do eventually when we go to our VS Code. But let's assume that this is done. So basically, the reason of doing this is to control the variance of the result of this matrix multiplied and the resultant of this matrix multiplication. So many a times the mean gets stayed put around 0, but the variance or standard deviation, they get exploded. So to control those, we do this scaling. So assuming that we have a single head self attention, we want to get the multi-head attention. So basically all that does is, if you see there is a concat operation being performed on top of multiple outputs from multiple dot product attention. So there are multiple self attentions heads operating, uh, and they give outputs which are concatenated and projected with a linear layer, and this is called multi-head attention. So there's nothing much to it basically, but yeah, let's go ahead and implement. So first up, we will do the scaling here. So when we are doing the calculation of QKT, we divide it by uh, output dimension of head size 0.5, or basically I think head size is given here. We memorize this head size parameter and we divide it with square root of head size. I hope this should work fine. Yeah, cool. It's working fine. While it's running, let's start implementing the multi-head attention. So here we need two inputs, number of heads and head size. So we defined multiple heads as a list of unindoled. My bad. Sorry, I kept on coding and I didn't switch the screen. Okay, so in the head class, I just memorize the head size here. That's a change. So you can see the diff in the VS Code here to understand what new code I'm putting in. And we put a scaling factor here, dividing by square root of head size to the way. Now we are working on our multi-head attention. So we use a nn dot module list, which is basically hold submodules in a list, which should be a kind of a list of modules. So what we are going to do is for h in for I in range and heads, this would be uh, head of head size equals to head size. Yeah, so we pass on this head size and we get a list of modules here. Let's look at the definition of this. So syntax looks something like, what does the syntax looks like here? Module list can be indexed like a regular Python list, but modules it contains are properly registered and will be visible by all. Methods, module methods. Okay, so we basically pass on something like this with a list of string and dot linear, this kind of thing. So this should all be wrapped up in a list. Once we have serve dot heads. So if you look at the paper, there was a concatenation happening on top of it, and then it was passed to a linear layer. Yeah. So projection equals to dot linear head size. We transformed into embed, right? Now let's define forward function. So what we do is self dot uh, so we iterate in the list of this heads, which is nothing but a list of the heads and head times, and for each of those heads we call forward method on X, and um, and this would give us a list of basically a list of outcomes, list of b by t by, so output of this is b by t by head size, right, divided by n heads. So we'll have to concatenate these to make b by t by head size. So we have to concatenate these on the last dimension to make uh, it head size. Therefore, cat dim equals to -1. This should give us this equals to self dot projection out. Yeah, so this should give us output of the multi-head attention. All we did is we passed in X into each of the heads. We concatenated output of each of the heads. So we got the output of b by t by head size and then passed it to this linear layer to get the n embed size. Now we have done this. Let's also uh, change this to self-attention heads. What happens here is this multi-headed attention. To call this, we'll need, mm, let's say we are doing 4 heads. And embed is 32. So we make this as embed divided by 4. Now I hope this should function. So in the last change after scaling of the self-attention weights, attention scores, we got this output 2.4483. Let's see if attend implementing multi-head attention is functional. So we got a few extra parameters. Oh, sorry. Self-attention heads. So self-attention heads, we pass it through self-attention heads. Output would be given to LM head. Now it should be all right. Thirty-two by 32, 8 by 32. Oh, okay. So I think there's a mistake in the projection layer configuration. So head size that comes here is 8. All right. So it should be still embed, because you are concatenating outputs of all these heads and then passing dimension, or that is of channel size and embed. Yeah, it should work now. Cool. It's working. So we have 8,700 parameters. Okay, so I just opened up the paper in the VS Code itself. It would be easy to switch screens. So you see in the model architecture, now we are done through with the implementation of this. Let me see if, yeah. So we were able to reach a score of validation loss of 2.31 further below, and we are generating this, still gibberish. Maybe we are starting to make sense. So we were able to implement this till now. Now what we have to do is, if we go at the higher picture, uh, we are done with this mass multi-head attention. There's another part in this block, multi-head attention, which is taking inputs from outputs of the encoder part, which is not needed because we are building on decoder only network. So this particular part we can ignore, and we can jump to feed forward part after this multi-head self attention. So we need to implement feed forward next. So for feed forward, what we need is to initialize is the output of this, which is of channel size n embed, is going into it. So we'll need to take and embed that dimension. This should be basically a linear layer with, or I think let's quickly go through the paper, what is happening in this feed forward somewhere. It should be shown. Okay, so here in feed forward network, what they are doing is each of the layers, attention sublayer, each of the layers in our encoder and decoder contains a fully connected feed forward network which is applied to each position separately and identically. This consists of two linear transformations with a ReLU activation in between. Basically, we have to apply two linear transformation and a ReLU activation in between. And this is applied individually to each position. So basically, after we are done with self attention and multi-head attention, we have done enough communication between the tokens themselves. Now we want to give time for each token to do some computation on its own representation after multi-head attention to get to a better representation basically. So here now what we have to do is basically, because we have to do two linear transformation, we should do this as an dot sequential and dot linear embed by n embed dot ReLU, and then again we'll have to do so this would be, let's say this is our net. When we call forward on this, just pass x to it. X is of dimension by this time b by t by an embed. So an embed will keep transforming to an embed and then out. So basically we have consists of two linear transformations with ReLU activation in between. We have done this. And also another thing we have to see is another way of this. While linear transformations are of the same across different positions, they use different parameters from layer to layer. Another way of this is two convolution with kernel size. T of input and output is when the inner layer has dimensionality of 2048. So basically input dimension is 512 and output dimension is 2048. So we'll have to change it to something like 4 times 4 times of this. Cool. All right, now we'll have to make changes to cell dot ff feed forward equals to feed forward and embed. So we, after self attention heads, we pass it through feed forwards and then we pass the output to lm head. Now let's try to run this and see if it's working. Okay, we reached to 17,000 parameters from maybe 8,000. We doubled on the parameters now. Last loss we were at 2.31. Let's see where do we reach now. Okay, the next thing in the paper now is organization, putting these things we have done. So we have done attention implementation. Okay, there's one thing. Uh, um, we employ a residual connection around each of the two sublayers. Let me first. Okay, so we are able to reach 2.288 with additional feed forward layer, which is again a bit improvement on our last score of 2.3155. So let's just check in this, commit this changes. Next up, we'll look at the two more important innovations that were crucial in helping to train the very long and deep neural networks effectively are residual connections and layernorm. So in one of our previous videos, we implemented batch norm from scratch. Batch norm is as we are averaging out, taking mean and variance across the batch dimension. In layer norm, we are taking mean and variance across the layer dimension. So basically, across each time step, we take the mean and variance to statistics to calculate to normalize the activations basically. So here what we are going to do is residual. So if you see, mm, okay, so add and norm. So basically this is doing some addition and normalization. Addition is something it's talking about residual connection, and normalizing is what is layer norm going on doing here. So let's first implement residual connections. So for residual connections, we would not need to implement any new class here, but all we have to do is um, after self-attention heads, let's say now we change the nomenclature now, x equals to token embedding plus position embedding. We do it this way. So this is basically doing the residual connection. We while after we have a representation from token plus position embeddings. We pass it through a self-attention head. We add that output of self-attention head to X itself. Then new X, we pass it through feed forward X, feed forward layer, and add it to the X again. So these are residual connections happening here, and I think they should work fine as is. Let's see if we can further get any improvement with residual connections. We can see a bit improvement again. From 2.28 we are to 2.23, and also the text looks a bit Englishy in nature. He, hey, yo, I with the throw honors, my lord, and whatever. So okay, so I think we can say residual connection gave us some improvements. Now let's so look at the paper again. Another thing is using layer norm on top of the residual connections. So you see we are using, after the residual connection, we are using layer norm here, and also layer norm after feed forward. So what we can do is we can add self dot ln1, because at two places we are doing layer norm. Mm, okay, yeah, I think we can do it. Layer norm 1, layer norm 2, and embed. And embed. So first layer norm will have to apply on outputs of this. And another layer norm would be applied here. So yeah, let's take it for a spin again. 2.23 was our last validation loss. Now next thing we'll have to do is, we have done this. So basically we have created a block. We have created each component in this block except this, which we are ignoring because we are focusing on only decoder model. So this residual connection and this connection we are able to complete. Now we have to put this inside a wrapper. Class will create maybe like named as block, and then we'll have to repeat this block multiple times as given in the configuration in this paper. So all these trainings I'm doing on my laptop right now, therefore it might be taking a bit longer than usual. 2.22. Okay, 2.22, which we can say is a slight improvement on the last score, which was 2.23. Okay, now mm, now let's get the paper. So basically, we want to wrap this entire thing into a block and repeat this block multiple times. That's what we want to do. Because after this, we are doing the linear head, LM head, anyways, and softmax is being done by the loss calculation. So we have to wrap this entire thing into a block now. Let's work on it. So for block, what would be the initialization parameter we would need is whatever is going in to the multi-head attention, which is n heads head size and n embed. Yes, number of heads, head size, and embed. These three parameters we'll be taking, and using these three parameters we'll have to initialize our so for multi-head attention, what we need is number of heads and head size, which basically is call. So if you see in this call to the class, hmm, I would like to change the implementation of this here right now because this is getting confusing. So maybe we'll say okay. So while creating the block, what we'll do is we'll just take the an embed and n heads as the input parameter, and we calculate head size equals to n embed divided by n heads. Once we have the head size, we define the self attention heads here. So we'll have to have multiple things: self dot ffwd, self dot ln1, self dot ln2. Multi-head attention here, and heads, and head size equals to an embed. For feed forward, we'll pass an embed. So we have this block ready. All the components that we need in a block, we call the forward on this. So x equals to x plus. So if you look at this picture, let me just pull it up here. All right. So if you look at this picture here, uh, after the paper, after the attention is all you need paper, there was a trend of doing skip connection and layer norm here after the mask self attention. But with time, this normalization layer norm has shifted before feed forward or before mask attention. So if you see in this architecture that is being used these days, uh, we do a layer normalization on the input, then it is passed through a linear layer, then all the self-attention, multi-head self-attention calculated. Then after linear layer, we just, after this feed forward, we drop out and do the skip connection and so on. So this is something that's slightly different. Uh, self dot self attention heads of self dot ln1 of x we'll have to do. So instead, if you see here, notice in our last change, we were uh, performing layer normalization after skip connection, but now we are going to do skip connection after layer normalization. And so x equals to x plus self dot dot ln to x. So this would just give us a final x out. So this is a block, and now we can remove all these things. Self dot blocks is, so basically what we want to do is we want to repeat this block multiple times. So say lab blocks equals to other block and heads. Uh, is any parameter and heads? Yeah, let's make this and head equals to 4. Now when we pass it here, n heads and n embed for range. So basically, how many times do we have to repeat these blocks is what we'll define as n layers. Let's say we'll repeat it 4 times or 6 times, or say 2 times for now, just so that I can run it on my laptop. So we'll basically for range and layers serve dot blocks equals to dot sequential arguments per blocks. So this would create a list of sequential module with a list of all the blocks basically. And output of this, what we'll have to do now is, we don't have to do any of these things, just cell dot blocks x. So this is quite simplified now. And I think it should work. Let's see, 2.22 was our last loss. Okay, so we are at around 49,000 parameters. We are getting some error. Let's look at this quickly. Thirty-two by 128. 32 times 4 is 128. Okay, we have created this variable here but not used it. So I think it should work now. 29,000 parameters. Last time it was 17,000. Now we are at 29,000 or 30,000 parameters. I'll just let it run. We were able to make further more improvements on the loss, 2.19 as compared to 2.22. This has come after addition of wrapping up all the uh, multi-head attention and feed forward layers into a block and repeating that block 2 times for now. So we are repeating it for 2 times. There are a couple of more things that we can sprinkle around here after multiple places, which is dropout and few more layernorm layers somewhere. So let's do it. Let's first define the parameter dropout equals to 20% of the random weights we will be dropping off. So first we can use an head, single head, out equals to dropout Then we can sprinkle it around after the projections in multi-head attention and feed forward attention as well. Feed forward. Mhm. Self dot dropout. And we can add one layer norm here as well. So we have sprinkled few more layer norms and also um, dropouts in feed forward and multi-head attention after all the activations or projections, and also in the single head attention. Let's see what happens now. Okay, it's training. We are at 29889. A few more, 100, 150 more parameters. Okay, meanwhile, let me commit this. Okay, so with this addition of dropouts and one more layer now, we're not able to achieve much progress, but this is it. So this is how a decoder only GPT kind of model would look like. And let's also, we've been still calling it diagram LM till now. Let's say GPT. Also, what we can do is we can try to scale this up and train this with a GPU machine so that we can figure it out. Let's say 256 is the block size, batch size at 128. Mm, These are okay. 10,000 iterations. This is also okay. And embed is 256. Number of heads is 6. Number of layers is 6. Mm, 256. So this would make our model to be exponentially high parameter counts now. Oh, sorry. Um, GPT. Right, it is 4 million parameters now. Okay, there might be a problem that an embed 256 divided by 6 might not be properly divisible. 256 divided by 6 is 40 is not properly divisible. 42.66, so 43. So therefore maybe okay, I just checked the number that 384 is what is properly divisible by 6. So that's what we'll keep as embedding dimension. Now it should work fine. So once we see that it's starting to, oh, all right, it is 10 million parameters. Wow. So we have jumped quite high now from maybe let's say 30,000 parameters to 10 million parameters. That's a lot. So it would take some time to train, and I'm not going to run it on my laptop. So instead let me connect to my GPU machine and run it there. Oh, I think my GPU machine is turned off. Let me turn it on first. I think there is some issue with my GPU machine. It is running, but I'm not able to SSH into it. But what I'll do is I'll um, run it after fixing it. I'll run the scaled up model on that machine and post the results on the GitHub repo. So yeah, that's where we conclude our GPT coding from scratch. Thank you so much for your patience and joining me in this journey. Next, I would like to scale this model up to level of GPT-2 by improving on each part of the models of the process, like tokenization, data, then each of the modeling techniques, etc. Thank you so much. Bye bye.